Hello, welcome back. So, we have come to the end of this course and today will be the last lecture. So, as such we started our journey from numerical solutions of ODEs and then we have moved to PDEs and we discussed various methods etc. So, I would like to mention few remarks and before that maybe we just briefly summarize how this course has proceeded and then some appendices which are kind of useful tools in addressing these numerical solutions. Okay. So, we started with single step methods for initial value problems. Okay. So, I will just put a summary quickly and then we move to the appendices. So, initial value problems. Okay. So, here we have single step methods and multi step methods. Then in multi step methods we have predictor corrector methods. Okay. So, then we move to boundary value problems. So, where we discussed finite difference, methods and shooting methods. So, in initial value problems the single step methods and multi step methods they are based on the principle of approximation by weighted average of slopes. So, this is by and large the principle, whereas in boundary value problems in finite difference the principle is approximating at various grid points. That means to compute a past value we need to compute at a particular grid point you need past several values. Okay. So, this is boundary value problems. So, this is with respect to ordinary differential equations. Okay. So, this is within the framework of ordinary differential equations. Then we move to partial differential equations. So, here we considered finite difference methods, for parabolic, then elliptic, then hyperbolic. So, while we have done this kind of so, this is method of characteristics for both first and second order hyperbolic. Okay. So, this is how we proceeded. Then we had to focus somewhere on iterative methods for sparse systems. So, this is typically when we deal with elliptic equations. Okay. So, we have discussed how each approximation occurs, and then how the error comes into play, and then convergence, stability aspects, etc. So, the aim of this course is, at the end of it, at least you get a better idea of what are finite difference methods for both ODEs and then PDEs, and to get a little advanced knowledge, so that you try to pick up and then maybe you concentrate on any advanced topic you can do on your own. Okay. So, at least you will be in such a position. So, with this definitely you are at advantageous position, because once you are done on your own and practice some examples, definitely you can pick up any advanced book covering advanced topics on numerical methods. As I mentioned, for example, how to solve problems on staggered grid, alternate direction and multi dimensions, and moreover, if you come across problems dealing with fluid mechanics, as you know, most of the studies these days are done numerically. So, you have to definitely have fundamental knowledge on various numerical techniques, and then definitely the advanced techniques. Okay. So, we come across some tools. So, throughout the course, as and when we met some technique, and then we had a brief discussion about them, and then proceeded further. But there are certain issues which I thought these topics should be put it as appendices, so that these are helpful. Okay. So, the first one is computing, say appendix A, computing eigenvalues. So, computing eigenvalues is a general issue which for stability aspects we have been doing, right. In fact, I have given this is a matrix and then these are the eigenvalues, but sometimes it is easy to compute, you can do it, but sometimes you have no clue. Okay. But there are methods, one of them which does iteratively is called power method. Power method to find eigenvalues of a matrix. Okay. Of course, this is iterative. Then when I say eigenvalues of matrix, we should put sum, because we can get only some of them. So, what is the idea? The idea is, given a matrix A n cross n, start with an arbitrary vector x and compute A x. Say A x equals to y. So, then what we do, normalize y by the largest entry. Say here y is y 1, y 2, y n. So, then you have to normalize by the largest entry, that means 1 over max of y I So, call this so y 1 max. So, this is y 1 y 2 okay. We normalize. So, you get some y star. Okay. So, then when you get y star, compute a y star equals to say y 1, then normalize y 1 by the largest entry. When I say largest entry in y 1. Okay. So, this we do, and then when do we stop? When so this process continues and then stops when the difference of normalizing factors, the difference of two successive normalizing factors is up to the accuracy. Okay. So, for example, so let us take an example. So, consider so this is a matrix. Then let us say random, we start with this. So, this is arbitrary. So, when we compute, we get 4, 3, minus 8. So, now the maximum entry in magnitude definitely is 8. So, we normalize. So, we take it common minus 0.3751. So, this is our y. Okay. What was the notation I have given? This is our y star, because we have normalized. So, this is our y star. Then we compute so, we do this, then we get 0.125 times. So, this time the normalizing factor is minus 5, and this is our say y 1 star. So, then again compute a y 1 star. So, this would be something like so, if we do we get after few iterations. So, after few iterations a on some y k star equals so, this is differing with the previous one. Okay. So, we stop here. So, that means we declare that is the largest eigenvalue and corresponding eigenvector is when I say we stop assuming the difference with the earlier factor is up to 3 decimal accuracy. You can compute and check it. So, we declare this is the eigenvalue, right. So, this is an interesting method. Of course, there is a proof why this works out and all that, but this is an iterative. So, this gives maximum, because every time you are normalizing by maximum and then we get that. Okay. So, now similar method can be used to get smaller, because you get the larger one and then invert. So, it is slightly in a different way. So, this is called inverse power method. So, our aim is this. Okay. So, this implies A inverse A x is A inverse lambda x, this is lambda A inverse x. So, this implies x is lambda or 1 over lambda x. Okay. So, now this is, so you are normalizing, okay, every time, right, but the inverse, computing inverse could be expensive. So, before power method is applied, inverse has to be done efficiently. For example, maybe LU equivalent of A. So, this is one suggestion. Okay. So, this is one appendix. I want to just give a brief idea on power method. Okay. So, then there is other one, appendix B. So, this is Ruth Hirsch criterion. So, many times in order to get the stability, we are ending up with a polynomial and then we have to find the roots of this polynomial, or sometimes the range. So, many times finding all the roots is quite complicated. So, at least if we can get the region where the roots lie, then at least we can conclude the corresponding stability. Okay. So, Ruth Hirsch criterion is very popular, and then it indicates how to compute the region of stability. Okay. So, let us have a look at it. Let P n zeta is n minus 1 equals to 0, be a polynomial of degree n. where nu I may be constants or functions of some parameters. Okay. So, now our aim is for stability we have to compute all roots. So, this is difficult. Okay. So, now what we are looking for? Aim. Interval of stability or values of the parameters for which it is stable. Okay. So, now this is done via transformation. Define transformation okay. So, if you define this transformation, what this does? So, real z and imaginary z. So, this part, that means interior of the unit circle onto left half of. So, we can write. So, interior of unit circle to left half plane, then I mean this is strict. So, the boundary, this is to imaginary axis, then point zeta equals to 1 to z equals to 0. Okay. So, now under this transformation, under the polynomial p n zeta defined in 1 becomes so it becomes this. Okay. So, now what we need is condition for the roots of 3 to have negative real parts, and hence, so this is we are looking for. So, Ruth Hirsch criterion ensures this. Okay. So, what is Ruth Hirsch criterion? Let p z is and is a determinant where A j greater than or equals to 0 for all j, then the real parts of the roots of p z equals 0 are negative if and only if the leading principal minors of D are positive. Okay. So, this is the Ruth Hirsch criterion. So, then accordingly we have, suppose k is 1, a 0 greater than 0, a 1 greater than 0, then k is 2, okay. Then k is 3, so these are the necessary and sufficient conditions, okay, for the real parts of star, real parts of roots of star, real parts of roots of star to be negative, and hence for stability as well. Okay. So, this is a general concept which is very popular for checking the stability regions. One uses Ruth Hirsch criterion, it is very standard practice. Okay. So, now the next is on bit on errors. Okay. So, because this is very important, sometimes what we do, an approximation could be a function and sometimes the approximation could be values at grid points. So, then maybe one expects a kind of a correlation between a correlation with the behavior of errors with the function notation as well as the grid notation. Okay. So, let us have a look at this. So, now okay. So, consider, suppose we have a solution of a numerical method is function u of x over some interval. Okay. So, this is suppose solution of a numerical method is function, then let numerical method be approximated by this. Then we define error function. Okay. Then we define max norm, then we define one norm, then we have square norm or Euclidean norm, and p norm. Okay. So, now these are errors with respect to functions. So, solution of the equation, okay, when I said numerical method, then numerical method is approximated by this. So, these are the errors with respect to functions. Now, errors in grid, okay, errors in grid. So, for example, say finite difference methods give ui at xi. So, for example, if we have a uniform grid, with n plus 1 equispaced points with h equals to b minus a by n and xi equals to a plus I h, where x 0 is a. Okay. So, we have u x approximately u 0, u 1, u n. Okay. Now, this we need to compare with a set of discrete values with the function. So, that means these ui's are nothing but, okay. So, these are approximating point wise, right. So, now define a vector e to be e 0, e 1, e n by e I equals to u I minus, I could have used capital, so that no confusion, I am using small ones, please understand. Okay. So, if we define this, then how do we talk about error? So, sometimes maybe averaging. Okay. So, u I is just point wise, but sometimes averaging. Okay. So, now since this is a vector, since E is E 0, E 1, E n is vector, one may be tempted to define the error function like this. Okay. But however, what will happen at each grid point, this one E I is the error. So, this will spoil the whole calculation. That means, if you consider this way, because this is n times the error at single grid point in some sense. So, therefore, this is misleading. Okay. So, what is the remedy? We have to normalize, we have not done, rather we are magnifying, multiplying it with n. So, this the remedy is because h the way it is defined. So, in some sense we are normalizing by n. So, then similarly for p norm, okay, because you can see h power 1 by p, this goes to 0 as p goes to infinity, right. So, this normalization works. So, that so what I am trying to say is the functions, we have defined these kind of norms for functions, but when it comes to grid, so similar concept may not be extended. Okay. So, this is one issue, and the other issue is norm equivalence. So, the standard definition is two norms are equal. Okay. Two norms are equal in the sense if there exists constants, if there exists C 1 and C 2 such that C 1 times with respect to one norm, other norm alpha for every x belongs to the corresponding space. So, for example, so if this is the case, then we say or equivalent, right. So, for example, so we take C 1 to be this and C 2 to be this. So, then if somebody concludes okay. So, this is nothing but root b minus a, right. So, what will happen if somebody this is equivalent, therefore, in this norm it is equivalent like this. So, then what would happen? This equivalence may not be carried because these things depend on n and h. Okay. So, the remark is since the quantities involve n and h, the above equivalence may not carry over, okay, when we discuss about error. So, this can be displayed by an example. So, consider and let the approximated is okay, say n even. So, if this be the discrete approximation, so this be the approximation on the grid with spacing h is 1 over n on this, let us say. Then define error E I h by so this would be half I is n by 2 0 otherwise. Okay. So, basically the function is like this. So, this is approximating. So, this is so the approximated is behaving like this, the stars, and u of x is behaving like this, right. But even if we refine, the grid, okay, we have norm E infinity is half for every h, but one is h by 2 and this is big of 2 as h goes to 0. So, which means this converges to 0, whereas this is not. Okay. So, the norm equivalence one has to be careful. Okay. So, this converges to 0, but this does not converge. Okay. So, this is a general appendix I thought I would mention, because in general we use power methods to compute eigenvalues, and then also the error etcetera are beneficial to discuss what kind of norm should be used. Okay. So, now some remarks. So, the remarks. So, we discussed finite difference methods. So, that is the highest when we started single step, multi step, and then we come to finite difference. Okay. So, there are higher order methods as well, higher order methods. What are these? So, these are typically they use better approximations to the second derivative. Okay. So, in what sense better? So, for example, if we consider u double equals to f of x, then usual central what we have been using Okay. So, now when we see this is nothing but a second order, right. However, u double x can be approximated by the following. U double can be approximated by the following, which is a fourth order approximation. Okay. So, accordingly, if we use this in place of this and then get it. So, you can see we expect more accuracy because it is spread over I minus 1, I plus 2, I minus 2. However, there could be difficulties because we may not be able to run the equation. It is a question mark, okay. Because see you have these points, okay, end points. So, they will increase the fictitious values. Okay. So, one has to take care of the corresponding issues, but however, such higher order methods are possible. Okay. So, then function space methods. So, typically we have the finite difference methods. So, these methods determine an approximation only at discrete grid points. Okay. However, these function space methods, they determine a function u of x on the entire domain that approximates the true solution. However, how this is possible? This is via, so this is via a system at a finite set of points by searching for the approximation u of x from a finite dimensional function space that is spanned by a set of basis functions. That means, so these basis functions are such that so it is approximated like this, and these are the basis functions. However, the task is how to compute Cj. So, this is the general task. Okay. So, then we have finite element methods. So, even finite element methods, these are nothing but approximate solution, that is a linear combination of some specified basis function. However, there is a slight variation compared to function space methods. This basis function is obtained something called weak formulation, and also there are finite volume methods, but another method I would like to mention before we conclude is boundary element method. So, for example, finite difference, these are based on grid. So, these are based on some triangulations. So, this can be thought of some triangle elements in case of finite element. So, this is boundary element method. However, what would happen compared to these two? So, the dimension would reduce dimension of the computation. Here for example, it is 2D, you have to completely handle the 2D domain even here, whereas here 2D means a line. Suppose it is 3D, you have to completely handle the entire volume, but whereas here a surface. However, these are good for linear PDE. What is the reason? The reason is these are based on Green's functions. So, if you have Green's function, so then only this boundary element method can be used, because one would end up with a boundary integral formulation based on the Green's functions. So, then you end up with integral equation on, for example, if the problem is 3 dimensions, you get an integral equation on the surface. If the problem is 2 dimensions, you get an integral equation on the line. So, then you just discretize using any general collocation methods and get the solution. However, there are restrictions of this as well. So, this is general idea of little more advanced methods. So, with this we come to end of this course. I hope you enjoyed hearing some of this, and your valuable feedback would definitely help. Thank you. Bye.